When you draw molecules in this way, maybe you think that they are static, but the fact is that molecules are in a dynamic motion and can adopt different conformations, which affect their reactivity. In this video, I will shed light on this dynamic behavior. Cyclopropane is a planar molecule. Since it's made of 3 carbon atom framework, we don't expect any dynamic motion of the ring. If you want to know more about this unique ring, check this video. So let's get cracking on cyclobutane. Assuming cyclobutane is a planar molecule, there will be perfect CH eclipsing along the carbon-carbon bonds. As a result, cyclobutane adopts pucker conformation. As you see, this conformation resembles a butterfly's wings. In this distorted conformation, hydrogen atoms slightly away from each other, so the strain energy resulting from hydrogen interaction in planar conformation reduces. Although puckering relieves eclipsing, it reduces bond angle to 88 degrees, which increases deviation from ideal tetrahedral bond angle. Unlike cyclopropane, cyclobutane undergoes ring inversion, a dynamic process that interconverts two puckered conformations. The energy barrier of this process is 1.45 kilocalories per mole, which is a very small value. This back and forth between two conformations is called butterfly motion. In ring inversion process, cyclobutane must pass from a planar conformation, which is a transition state. The ring inversion is such a speedy process that it makes sense to consider cyclobutane as a planar ring, which is average of the two puckered conformation. If you want to know how much is the smallest energy barrier, check this video. Although 4-membered rings have a slightly bent conformation, the corresponding lactones are flat. For example, in this lactone, using LDA as a base, the corresponding enolate is produced which can react with electrophile. In this case, isopropyl group dictates the stereochemistry of the product. Because of steric hindrance, this face of the molecule is blocked by isopropyl group, so attack occurs from the other face. Since the double bond in enolate is planar, the stereochemistry of phenyl group in a starting material is not important. Now let's discuss the stereochemistry outcome of this reaction. Reduction of substituted 4-membered ring ketones is usually a stereoselective. As you see, in this case, cis product is favored. This ketone has a bent conformation similar to cyclobutane. Like previous example, the isopropyl group blocks this face of the molecule, so nucleophile attack to carbonyl group occurs from the opposite side. As a result, hydroxy group and isopropyl group are in the same side of the product. Although bond angle in planar cyclopentane is near to the ideal tetrahedral, as with cyclobutane, it suffers from eclipsing hydrogen interactions. By distorting, cyclopentane relieves eclipsing. In envelope conformation, 4 of the carbons are in approximately the same plane, and 1 carbon atom moves out of the plane. As a result, there is a balance between increased angular strain and decreased torsional strain. Alternatively, cyclopentane can adopt half-chair conformation, in which 3 atoms remain on the same plane and 2 atoms are above and below the plane. The envelope conformation is 0.5 kilocalories per mole more stable than half-chair conformation. This is such a small value that cyclopentane is in rapid conformational flux. This conformation change leads to successive oscillatory up and down movement of the 5 carbon atoms of cyclopentane in a direction perpendicular to the plane of the ring. This process has been called pseudoration. The energy barrier between envelope and half-chair form is so small that there is no natural conformation of the 5-membered ring, although substituents can increase this energy barrier. In pseudo-rotation circuit, there are 20 conformation minima. In envelope conformation, each carbon atom can be placed above or below the plane, resulting in 10 conformation. Unlike cyclobutane, cyclopentane never adopts planar form to ring inversion. Instead, it passes from half-chair conformation. So between each 2 envelope forms, there is 1 half-chair conformation. The remaining 10 conformation minima comes from 10 half-chair conformation, lying in between 2 envelope forms. At any one moment, one of the carbon atoms is at the point of the envelope. But rapid ring flipping equilibrates all these conformers so that all 5 atoms are on average the same. Although cyclohexane can exist in different conformations, the chair form is the most stable one, because of minimum angle strain and eclipsing hydrogens. Substituents in chair conformation can be placed in axial or equatorial positions, so in cyclohexane there are 6 axial and 6 equatorial hydrogens. Cyclohexane is involved in a dynamic process which is called ring flip or ring inversion. in which axial and equatorial substituents exchange their positions. Ring inversion is not a simple process and involves with many conformational changes. In the first step, one half of the molecule becomes planar by moving up the foot-rest carbon atom, while the other half of the molecule remains in chair conformation. So this form is called half-chair conformation. If this carbon atom continues to move up, we arrive at Bose conformation, which suffers eclipsing 6 hydrogens. In addition, there is a characteristic strain between 2 hydrogens which is called Flagpole interaction. Cyclohexane reduces strain by twisting. As you see in twist-Bose conformation, hydrogens are not completely eclipsing, so this form is more stable than Bose conformation. After being twisting, this carbon atom becomes planar, so the molecule passes from another half-chair conformation. Finally, the ring inversion process ends up with moving down this carbon atom. Although chair conformation is considered as the most stable form, substituents play an important role in the stability of conformations. So chair form is not always more stable than other conformations. For instance, cis-1,4-diethybutyl cyclohexane in chair conformation suffers a steric hindrance between one of the methyl group and 2 hydrogens in axial position, while this strain does not exist in twist-Bose conformation, when 2 tibutyl groups are in the pseudo-equatorial position. So in this case, twist-Bose conformation is more stable than chair form. From introductory organic chemistry, you know that bulky substituents prefer equatorial position of chair conformation, since in axial position, steric hindrance between bulky substituent and hydrogens of the cyclohexane ring unstabilizes the molecule. Now look at this molecule. In the first side, you may think that phenyl group is larger than methyl group, so occupies equatorial position, but the fact is that phenyl group prefer axial position. But how is it possible? First off, let's place phenyl ring in equatorial position. It is important to note that phenyl ring can orient in 2 ways. In one of the conformers, plane of the phenyl ring is parallel to bisector plane of the cyclohexane. In this conformation, orthohydrogen of phenyl ring and axial methyl cause serious steric interaction. The second conformer is achieved by 90-degree rotation of the phenyl ring. In this conformer, there is a steric hindrance between 2 orthohydrogens of the phenyl ring and 2 equatorial hydrogens of the cyclohexane ring. In addition, both conformers suffers from 1,3 steric hindrance between axial methyl and axial hydrogens of the cyclohexane ring. Now let's place a phenyl group in axial position such that the plane of the ring is perpendicular to the bisector plane of the cyclohexane ring. In this conformation, the only steric hindrance arises from interaction between 2 orthohydrogens of the phenyl and equatorial hydrogens of the cyclohexane ring. As you see, the molecule is more stable when the larger substituent occupies axial position.